And then all of a sudden they're like, hey, we need you to maybe, I can't go into details, maybe hack some satellites. So, I have to learn this stuff myself. And I'm one of those people who believes that you remember about 10% of what you're taught and about 90% of what you teach. So once again, I'm going to stop this share, go over to my browser. And we have a CTF for everyone here to do while I'm giving a presentation. And by the way, don't feel like it's rude to ignore me. If there's something you already know, just ignore me and focus on the CTF. So we have some challenges for you to do on samclass.info/space. And the way you do this is you click on a exercise like SP100. And at the end, there's a flag. And you find the flag, and then you would click on Submit Flags, make sure you're on SP, select the challenge 100.1, add your name. So in this case, it would be, I don't know, it can be any name, like Hacker 100. And then you would add the flag. So you'd say, it's definitely not a typo I want. Push Submit. And it says, oh, answering correct. So, but if you got it correct, you would then go on to the scoreboard. Anyway, back to the presentation. Stop share and all right, so part one, getting into space. If you wish to make an apple pie from scratch, first you must hack the universe. So let's talk about how we actually get into space. They say don't put equations into presentations, but this one is so important and so critical. This is called the rocket equation. Basically what this means is that your quote unquote delta V, this is a very important term in rocketry, is equal to your initial mass over your final mass. So basically what you want to do is you want to, your total amount of basically what this means is that your total amount of change in velocity has to do with how efficient your engines are, how much your initial mass is, and how much your final mass is once you've used up all your fuel. And I see we have something in the chat. I see secret squirrels in this. What secret squirrels in the side thumbnails? Oh, I see. Oh, that's fine. That's fine. That's fine. Good idea. Someone says that I'm exposing critical information in the thumbnails. That's fine. Anyway, so important rocketry terms. So we already talked about delta V. That means change in velocity. We also have to talk about specific impulse, which just means engine efficiency. Something with a high specific impulse uses very little fuel to get a lot of delta V. Something with very low specific impulse or very low engine efficiency uses a lot of fuel and doesn't get much delta V. TWR stands for thrust to weight ratio. So sometimes we put rockets in space or spacecraft in space, and they use something like an ion drive. But why don't we use an ion? Because it has a high specific impulse, right? So it uses very little fuel, but gets a lot of delta V. But unfortunately, the thrust it produces is so low, you can't get off the ground. So that's where thrust to weight ratio comes in. Sometimes you just need a lot of thrust, to counteract gravity. But once you're in space, it's not an issue. And then because of this, because we have, your initial mass and your final mass, the way that we do sort of rocket configuration is we have it in stages. So you start off with like the big rocket, you think like the Saturn V with the big rocket, it goes up and it has all this fuel, and on top it carries a smaller rocket, and it's like a nesting doll, and you have a smaller rocket on top of that. So the initial mass is smaller, and then the final mass is even smaller, and you just kind of jettison the parts of the rocket that aren't necessary anymore, and that's called staging. And so once you get into orbit, you basically orbit in an ellipse, right? I'm sure you've heard about this before. And maybe you've heard the terms like apogee and perigee. And what those means is that part of your orbit is going to be closer to the main orbital body. So in this case, the Earth. So like, let's say we're talking about the Earth. So when you are close to the Earth in your orbit, that's called the periapsis or the perigee. And when you're far away in your orbit, that's called the apoapsis or the apogee. And keep in mind that all free fall is an orbit. It's just most orbits you're aware of just hit the ground. So if I toss an object in the air, and the green screen is gonna not like me for this, but when I toss this bottle in the air, its apogee was just right there, just a few inches, above my head. And then of course, if it could fall through the earth, it would, and then come right back up to me. But of course, it doesn't fall through the earth, it hits the ground. And of course, not all spacecraft, not everything orbits goes around the equator. So sometimes you have an angle of inclination, and those are important to know about too in satellite hacking, because a lot of the weather satellites and a lot of the geocommunication satellites that are in low Earth orbit actually have a very polar orbit. So the angle of inclination is almost at 90 degrees. So it's going almost north to south around the Earth as the Earth rotates. And this is so it can cover as much ground as it can when it's taking pictures. So yeah, let's look how things get into space using my favorite program, Kerbal Space Program. I'm going to stop the share, open up a video, I think. Here we go. All right, and I'm going to redo the share, I think. Share. It's working, perfect. So here we have a rocket that I made in Kerbal Space Program. And for people that don't know, Kerbal Space Program is a video game essentially, but it allows you to design rockets and shoot them into space. And here I made a very simple rocket to go over sort of the stuff we talked about before. So I know it's hard to see, but up in this window at the top right is where I'm mainly looking at my delta V. So how much change in velocity I can get out of this rocket. And that is the main stat that you're concerned about when you're making rockets. And of course, like I said, you do concern yourself with the thrust to weight ratio when you're lifting off. But other than that, it's always just delta V, delta V, delta V. How much change in velocity can you get out of your rocket? So we'll take this to the launch bay, and we're just going to lift off now. So we start. Why we want to go straight up first is because gravity is not the primary obstacle of getting into space. It's the atmosphere. We want to get through the atmosphere as soon as possible. As when we start going fast, like bullet fast or speed of sound fast, the atmosphere stops becoming like this thin, wispy thing and starts becoming more like a soup. So we got to just punch through the atmosphere as soon as we can. And as soon as we get to the upper atmosphere, you'll see we'll start turning in about 45 degrees. And this is what, of course, rockets in real life do too as well. And the reason why we want to do this is because our end goal is to circularize the orbit. If we were to go straight up, we would just come straight back down normally. But we want to get into an orbit. So we actually want to go up and then towards the east. I don't know how to. And so you'll see right here is when we jettison the first stage. So we ran out of fuel with the big rocket at the bottom. We jettisoned it, and now we have a much smaller rocket, but that is going to take us the rest of the way into space. And that's what I was talking about staging. So we have this much smaller rocket now, and now we're going to sort of position ourselves so that we're horizontal. So all our energy is going to go towards circularizing the orbit at this point, because our apogee, our apoapsis, is now high enough. And we have somebody in the chat. Okay, thank you. Someone in the chat want someone to mute themselves. Okay, so we are now in orbit. We're getting ready to circularize. So here we see a map. And at this map, I'm going to say at the apoapsis, at the apogee, start burning. That's essentially the plan I'm making. And so the way that orbital mechanics work is that what you do on your end of the node affects what happens at the opposite end. So remember when I said that all free fall is in orbit? In this case, you can see that we're in what's called a suborbital trajectory. So we would go up, we would hit the apoapsis, and then hit back down. If the Earth or planet wasn't there, we would, of course, go through it, go back, and back into space. But what we want to do is we want just to extend the orbit out. And so that's what we're going to do. We're going to wait until we're at the height of our orbit, and then we're just going to thrust eastwards and circularize the orbit, which is going to affect the opposite side of the orbit that we're trying to get to. So we do that, and we grow our orbit, we keep thrusting, and then eventually, we stage again. So we're now a nice small rocket, and we circularize the orbit. And that is how things essentially get into a stable orbit. And once it's there pretty much for good. Now, in a low Earth orbit configuration, satellites do hit the atmosphere because there's no set boundary between the atmosphere and space. For example, recently we, of course, had to deal with the Chinese rocket that was going to land somewhere, anywhere. We didn't know where. And why was that? Well, that's because what happens is that the sun hits the planet, and that causes the atmosphere to expand in unpredictable ways. So if you're in a low Earth orbit, you will eventually decay from the atmosphere sort of expanding, and you get little whiffs of air slowing you down. But of course, if you get out far enough, like you are halfway to the moon, you're basically there for good. And this is why space junk is a problem right now, is because we put this stuff up there and it's not going to come down, right? If it's far enough away, it's just going to stay up there. And if that stuff breaks apart, the stuff that breaks apart is going to stay up there. It requires no energy to stay in orbit. You're just falling around the Earth over and over again. All right, so any questions so far? Yes, so we are at that point, we would be in a low Earth orbit, or in that case, a low video game orbit. To get into a higher orbit, of course, you would just extend out your apoapsis or apogee and sort of do the same thing again, right? It's the same process, but the difference between a low Earth orbit and a high Earth orbit is just the apogee and, of course, the perigee. If those things are far out, then you're good. And I don't know if there's any sort of set definitions for low Earth orbit versus high Earth orbit, but the way that I sort of think about it, and you can see this on maps too if you look at where all the satellites are. You basically have a bunch of low Earth orbit satellites, and the way that I define that personally is they are going to slow down and fall back to Earth eventually because the atmosphere is dragging on them a little bit. So like the International Space Station is also not just a space station, but a spaceship. And they actually have to have thrusters to keep themselves in orbit because they are so low that, like I said, the Earth's atmosphere will expand and slow them down slowly over time. And so therefore they are in a low Earth orbit. Something like GPS, which is a bit further out, doesn't have that drag. So the GPS satellites are going to be out there, goodness knows. And then further out from that, of course, are the geostationary satellites, which we'll get into in a little bit. All right, so let's go back to the presentation. Oh, I think someone wrote something in the chat. Oh, yes, Wikipedia does have a great map of orbits. Perfect. And Chris says, Wikipedia says, low Earth orbit is defined as an orbital period of 128 minutes, I guess, or less. Yeah, okay, so there are some good defined limits. Excellent, thank you for that. All right, so now we know how rockets work. So let's get into space hacking, cybersecurity in space. So the cosmos is also within us. We are the way the cosmos can hack itself. So how does the communication process between a space vehicle and a ground station work? Well, first you have, your mission control center, your flight control center, right? And then that usually gets the data from that goes through some cryptography process through an SDR. Yes, one of those SDRs, like you might have, same thing, to an antenna. And then, of course, then that gets wirelessly transmitted to the space vehicle, right? And then just does the exact opposite process. So it takes the data from the antenna, pumps it through an SDR undoes the cryptography, and then sends it to like the data handler and the flight computer. And it's really that simple of a process. And so if we look a bit closer at the space vehicle bus, so we have at the left, oh, SDR. Okay, thank you, Leandra. Sorry. Yeah. What is an SDR? Okay, thank you. Sorry, I sort of assumed everyone knew what that is. That's a software-defined radio. And we will talk about that in a lot, actually, in this presentation. Basically, the way traditional radios worked is you would have a radio device, like an antenna, connected to some hardware that would do something like decode FM signals coming from your local radio station, right? So like Wild 94.9 FM. The way that would work is you would have dedicated circuitry that would take in the 94.9 megahertz signal, FM signal, pump it through a circuit that would turn it back into audio. What a software-defined radio does is it just takes in the raw signals from the radio and sends it to the computer. The computer then figures out, okay, well, I'm going to decode this as an FM signal and pipe it through like the audio of your sound system. And that's one of the things that you can do right away if you get like an SDR dongle, a USB software-defined radio dongle, is of course tune into your favorite FM radio stations right on your computer. And yes, so yes, most SDRs are USB dongles. I am coming around to the idea that the best SDRs actually are Ethernet based for reasons we'll get into later. But yeah, the cheap ones you can get for like 20 bucks. USB, they're fantastic. And we're, like I said, we're gonna go over this a lot because SDRs are everywhere in space vehicles and ground stations. So on the space vehicle, we have the data coming in from an antenna going to an SDR, so it's all programmable. We don't have any fixed, paths. We can program it to handle any sort of radio we want it. We can do FM demodulation, AM demodulation, change the frequency, whatever. It's all handled in software. That goes to a data handler, and that figures out where it's supposed to go because we want to have as much separation on the bus as possible, right? This is for security reasons. We don't want the sensors being able to tell the thrusters what to do, and vice versa. We don't want the thrusters interacting with the sensors, sorry, someone's writing something in the chat. Space LA shenanigans. Okay, Murdoch's someone wants us to read Murdoch's Pirates. I've never heard of that before. Some applications. Yeah, okay. All right, well, thank you. By the way, before this started, I said anyone who has anything, feel free to interrupt me during the presentation. This is the best way to go, I found, in online presentations. Anyway, so yeah, you want to keep everything separate. And you'll notice there's a few things up at the top here. And I kind of want to explain what these are. So what is a torque rod? Well, if you're in a low Earth orbit, you can still be affected by Earth's magnetism. Well, that means that if you want to rotate your ship or your space vehicle, so it's always like, for example, facing the Earth, you can have what's called a torque rod, which are basically just magnetic rods that will keep your spaceship oriented in Earth's magnetic fields, right? So it's basically just like a compass in space or a compass gyroscope thingy in space. No energy needed, and you can keep your spacecraft oriented correctly. It's one of the benefits of low Earth orbit. And then next to that, we have flywheels. So let's say we're not in the vicinity of Earth. Well, what you can essentially have are a bunch of gyroscopes, right? They just spin around, spin around, spin around. And you can use that to essentially then stop them and then have the spaceship like tilt or twirl in any different way. Rotational velocity is basically free or very cheap in space. It's only moving back and forth that takes fuel. And then for that, like I said, if you want to move back and forth, we have RCS thrusters or reaction control system thrusters. These are usually monopropellant, hydrazine type thrusters that just tell the spacecraft to move left or right or alter the rotation. Sometimes flywheels gets what's called saturated, and so you need the RCS as a backup to stop some rotation. And then of course you have the thrusters too. So if you want to boost your orbit or or go down in orbit, you have your thrusters on your space vehicle. And those are the main components. And of course, we have, our payloads and sensors, right? So if you're going to send something into space, it's usually going to have a camera, or who knows. Are flywheels used for energy generation too? No, they are not. They take energy. I suppose you could use them for some sort of like re-energy taken. I don't think that would, I think that would probably complicate it too much. But they generally run on electrical energy. Usually for spacecraft, that's going to be generated by solar panels, sometimes by radioactive batteries, which we can talk about later. But the way it works is, like I said, it's just gyroscopes. That's all flywheels are. They're gyroscopes in space. And on Earth, we can use flywheels, of course, to generate power and to maintain power. You can actually do some really cool things with flywheels. If you get a big enough one, you can spin it up, and then it maintains that it maintains its sort of angular velocity, and then it becomes really hard to stop. And it's one way of storing energy. But in space, flywheels are just for maintaining orientation. All right, let's move on. Clear all drawings. How do I stop drawing? Mouse, there we go. Let's see. Okay, so we already talked about low Earth, medium Earth orbit, and geostationary orbit. So low Earth orbit, like I said, very low, interacts with the atmosphere. Medium Earth orbit are like GPS, where you have things sort of in the middle. Geostationary orbit means that the orbit is so far out from Earth that it takes exactly 24 hours to orbit. And that means that if you are looking at the satellite from Earth, it appears to stay still in the sky. And so all geostationary orbital equipment is in this thin band, all circling the equator. Because if it had any incline in the in the orbit, it would sort of bob up and down in the sky, and we don't want that. So all of them are in this big circle, like a ring around the Earth. And of course, we have deep space. So those are things that are far away, like things at Mars, things at the moon. Those all go through deep space, and we'll talk about that later as well. So what could possibly go wrong with going to space? Well, it turns out a lot. Basically, space is a series of unfortunate events. Whatever can go wrong will go wrong. And it's amazing anything still runs. Because if you think about it, right, we're putting equipment in space and then having it run for like 20, 30, 40, 60 years in the case of like what, Voyager? Voyager 1 and 2 went up in the 60s, 1960s. They're still out there sending back data. So a lot can go wrong up there, right? You have a lot of radiation that can fry the electronics. You have temperature swings, right? So it can go from like negative, 200 degrees Celsius up to 400 degrees Celsius. You have collisions with like asteroids and mini asteroids. You have collisions with other satellites, which can cause something called Kessler syndrome, which is where there's so much space junk that we can no longer even get up into space because everything will just hit you, right? That's why space junk is a problem. You can lack testing due to expense, right? Because it's how hard is it to test a rocket or test a piece of space equipment? You have to have very specialized, equipment to do that, specialized conditions. Launch vibrations, of course, rockets, are just really powerful and they're shaking, and that can destroy your satellite. And of course, sometimes things just don't get off the launch pad, right? Things either don't get into space, they explode on the launch pad. It's pretty awesome, but unfortunately, if you put 2 years of your life in a robot going up into space and it blows up on the launch pad, well, that's life. Not much you can do about that. Of course, sometimes the space vehicle fails to deploy. The solar panels don't unfurl. Sometimes we were talking about controlling the rotation. Sometimes it's just uncontrollably tumbling. You can't get the gyroscopes online. You can't get the flywheels to work, right? Sometimes you can't get it to power on. Sometimes its own electronics doesn't, interferes with its ability to contact Earth. Sometimes it just deorbits because it doesn't get into high enough in orbit. Or the anomaly might destroy equipment. Uh-oh, what did I just talk about there? The anomaly. So this is something I learned recently in the past year or two. There is something called the South Atlantic anomaly. Basically what this place is a region over South America where things just go wrong, likely due to abundance of radiation. Of course, when the The Earth has a magnetic field, and it fields radiation coming from the sun into very specific regions. So there's the South Atlantic anomaly, and you can see in this picture to the right here, where if there are electrical failures on spacecraft, it almost always happens in this region here because of the anomaly. Yeah, it's sort of like the Bermuda Triangle, as some people are saying. But this is real. This is not something, that is, made up or a legend. This thing is, you really have to protect your spacecraft. And of course, things go wrong a lot. So with that in mind, and you can't go up in there and fix it, right? You can't go up into space and be like, oh, well, my spacecraft is now defunct. What am I going to do? So unlike ground computers, cyber attacks are not the primary threat to operation, right? You have all this other stuff going on. In addition, traditional malware is anti-malware stuff we run on our normal systems are impractical due to power and resource usage. A lot of these systems use chips that were developed in like the 1980s because they're proven, right? You can't have the newest technology going into space because you don't know if it's going to withstand space. So you really need robustness and isolation, right? You got to have your spacecraft be able to be hacked, but then be unhackable, right? Have it be able to resume from a bad situation. And of course, like I said, isolate your components. So you have your bus and make sure that the camera can't talk to the, thrusters, for example. Many spacecraft, okay. This gives me nightmares. But this is known publicly, so I can tell you this. Many spacecraft will deliberately disable encryption if the space vehicle cannot communicate with anything on the ground. Okay, so let that sink in for a minute. If you have almost all the equipment in space, have a fallback mode where all the encryption will be turned off if you can jam their signal for long enough. Oh, Jesus, that's not good. But that's the way things are. And you just have to have that fallback, right? Because so many things can go wrong. And like I said, cybersecurity is not the #1 destroyer of satellites in space. But what can a threat actor do? What can a attacker of satellites do? Well, they can tell the payload to use all the power. That has been used in the past. Basically, what you do is you tell the flight computer, as soon as you boot up, run all the equipment, take all the pictures, send everything to your ground station as fast as you can, so that the space vehicle boots up, it runs all the stuff, and then of course it runs out of power, shuts down again, and then it tries to do the same thing, shuts down again, and it's stuck in an endless loop, and you essentially denial of service the whole satellite. And that has been done before on real satellites. You can of course compromise the software-defined radio, change frequencies, that kind of stuff. You can interfere with the navigation data. So the way that satellites in space know where they are is through star trackers, which is exactly what it sounds like. It just looks at the positions of the brightest stars, figures out where it is. It can figure out where it is based on the sun. That's another good big ball of light that can be used to figure out where it is. Or through GPS. GPS works in space as well. It's not just a ground thing. So a lot of the low Earth orbit satellites, for example, have GPS receivers on board to figure out where they are. And of course, you can use thrust to mess up or deorbit the satellite. You can permanently disable communications by reprogramming the computer or something. Of course, we already talked about jamming. You cannot use certain anti-jamming technologies in space for various reasons, unfortunately. So for example, on drones, you might find something like a frequency hopping spread spectrum system. I'm not going to get into details about how it works, but essentially it just hops around all these frequencies. But because in space, you're sharing all those frequencies with all the other stuff, that becomes impossible. So all the satellites are susceptible to jamming of some kind. And of course, other countries can interfere or steal with the design. So we have, like SolarWinds, supply chain vulnerability. Yes, is it only NASA or other tech as well? Yes, this is for this. All this applies to NASA and other agencies like SpaceX, private or otherwise, JAXA. All this applies to everyone. Everyone's sort of in the same boat. So what can a threat actor do? Again, sort of once again, poison the supply chain, poison test data. So you think your spacecraft works, but it doesn't. Take over a ground station. So you have to, part of maintaining cybersecurity in space is making sure that your mission control center is as secure as possible. And of course, just install malware on the bootloader of the machine. They get on, they control it, and then rewrite all the software and have a new encryption scheme ready to go. Do most satellites use GPS? So it depends on the satellite. Low Earth orbit satellites, generally, yes, you do use GPS. Of course, once you get out of low Earth orbit, the main thing, of course, are sun trackers. And if you are going way out into space, you would use a star tracker, generally. But of course, you can use a star tracker in any orbit. Or a sun tracker. The only thing, of course, is that if you're near the Earth, then the Earth is going to be blocking about half your view half the time, or all the time, I should say. So GPS works really the best if you're in a low Earth orbit. And of course, sun tracking is really good if you roughly know the position of the satellite. You just, need to, have it look at the sun. And of course, if you're going way out into space, where you sort of need, just where you're not gonna have much interference and you can just see all the stars very clearly, then the star tracking is the best. But of course, you can combine it too. You can't beat a sextant and hourglass. Yeah, so actually, no, this is really funny because, a lot of the old techniques that we used for navigation of ships back in the day is what we're using to navigate our spacecraft in space. Nothing really gets old, just evolves. All right, so what can we do? So what can we do to protect our spacecraft, right? So we can have watchdog scripts and programs that make sure everything is going hunky-dory. We can have gold copies to fall back on. So if something goes bad on the spacecraft, we can have a way for it to reset to a known good state at all times. We can have fallback encryption. So if a encryption scheme fails, we have another set of encryption that we can use instead. Before going into full decrypted mode. The one thing that is very important, of course, is to have resource limits, right? Have sanity checks to make sure that the spacecraft is only doing what it is expected to do. And of course, isolation of buses and resources. So one thing does not affect another thing if it gets compromised. And so someone asks, are most satellites located in low orbit? Absolutely, yes. The vast majority of satellites are in low orbit. This is for a couple of reasons. One, it's cheaper. That's the number one reason. Let's not kid ourselves. It takes less fuel. It is cheaper to get to low Earth orbit. But the other, of course, benefit is that there's less lag, right? If you are putting up Starlink, for example, and they're putting up like 600 or over 600 Starlink satellites, just for the SpaceX internet space thing that they're putting up, over 600 so far of these satellites in low Earth orbit. And because they're in low Earth orbit, there's less lag. The speed of light actually becomes an issue as soon as you start talking about distances in space. For example, if you're talking on the moon, it takes about 1 to 2 seconds for light from the Earth to get to the moon, another second or two for the light to get back. And of course, if you're in geostationary orbit, it takes not a second, but quite a few milliseconds, to get to a geostationary satellite. And so if you're using a geostationary satellite for internet, that adds a lot of latency. So there's a lot of good reasons to put things in low Earth orbit. But of course, for me, the biggest one is that things in low Earth orbit will eventually fall back to Earth, which is what we really want. We don't want things staying in space forever. So yeah, let's hack some satellites. What do you say? Specifically, oh, sorry, someone wrote here in the chat, is there any website? Yes, we'll go over that in a bit, some websites that have this information. Specifically websites about space vehicle defenses like the page right now. I don't know too much. There are a few books about space hacking. I don't recommend most of them. They're pretty bad. I would say if you want to learn about space hacking, join your local radio club. That's where all the information is kept. Get a ham license, join your local ham radio club. There are people there that know everything about space communications. Yes, ham radio. Get your ham radio license, join a ham radio club, and that's where you're going to get a lot of this information. Unfortunately, I don't know of any really good sources for a book that'll say like, here's how to hack satellites. I should write one, but I'm not at that point yet. Anyway, so let's hack satellites. So we are all related to each other biologically, to the Earth chemically, and to the rest of the universe via software-defined radios. So like I said, we're going to be talking a lot about software-defined radios in this talk. So let's talk about light polarization. So when we're talking about software-defined radio, we're really talking about receiving radio signals. And radio signals are light. Okay, there's no difference other than frequency between light and radio waves. So, and like light and radio waves can also be polarized. So for example, television broadcasts use what are called horizontal polarization. So you can think of it like spreading out horizontally from the ground. If you have what's called a dipole antenna, and let me stop the share here for a second, so you see my video. Let me pull out the dipole antenna. Okay, so this is what's called a dipole antenna. Basically, it is, and I'm sure you've seen these before. You have two ends here. And maybe if you have had a TV in the past, sorry, you can't see this very well. Maybe if you had a TV in the past, it would look something like this, right? You would have like rabbit ears pointing up. Now, what they don't tell you is that if you actually want the best signal from your TV, you would want the antenna like this. Why would you want the antenna like this on top of your TV and not like rabbit ears? Well, that's because the signal coming out from your local TV station is actually horizontally polarized. So it's coming in sort of like this, right? Left to right, left to right, left to right, left to right, right? And you can also have vertical polarization where the signal's coming in up and down, up and down, up and down, up and down. And that's what we're talking about polarization. And that's really important because if you want to get the best signal, you really want to know what polarization this signal is coming from. Let me go back. I did not do that correctly, apparently. It's missing. But anyways, that's how it works. I'm not gonna waste your time by debugging that since it's pretty much done anyway. But yeah, that's all it takes to decode the sound file. So you take the sound file, you put it into this program, and you get a black and white image. Well, two images technically. And that's called automatic picture transmission. And you'll see those a lot on weather satellites. And if you're going to start hacking weather satellites, that's the perfect place to start. Those sounds come in loud and clear. You can just put on a pair of headphones while you're listening on the SDR. You can see it, you can hear if it's coming in clearly. And then of course, it's fairly easy to decode. So let's go back to the share. Here we go. So let's talk about that SDR again. So when we're talking about space satellites, like think about this for a second. We want to tune in to something that's, I don't know, 1.2 gigahertz. That's impossible. We can't put a 2 gigahertz signal over USB, for example. That's not going to work, right? We can't just directly do that. USB runs at something like 24, megahertz or something alone, and you can't push a 2 gigahertz signal through USB like that, just straight up. So something has to be done. There has to be a trick, and of course there is a trick because of course we do have our software-defined radios, and that trick is that we can multiply a signal coming in with another signal, and what we get out is the initial signal minus the signal that we created. So in this case, oops, we have someone in the chat. NOAA satellites are still working and are up to 20 years old. Yes, some of the satellites are up to 20 years old. NOAA satellites do get refreshed frequently though. So some of them are very old, although the ones like NOAA 17 and 18 and 19, those are relatively new. But some are old. And someone heard NOAA 3 the other day that was put up or a few weeks ago, that was put up in the 1970s. And that was so exciting. Can you imagine having this computer put up in the 70s, starting to send signals down? I mean, oh my God, talk about great hacking time. So yeah, so you have a signal coming in from the antenna, and you have a signal we create and we multiply it. So like, let's say we have 2.1 megahertz, right? Or gigahertz, 2.1 gigahertz signal coming in. And then we have, say, a 2 gigahertz, about a 2.5 gigahertz signal that were generated. That gets multiplied, and 2.1 minus 2.05 equals 0.5 gigahertz, or much, yeah, 50 megahertz essentially. Thank you. Yeah, so we get 50 megahertz. 50 megahertz. So now we've essentially created a 50 megahertz version of the initial wave. Now, of course, we actually get two things. We get this in minus and this plus. But if we use a low pass filter, so we say anything under, say, 70 megahertz gets filtered out, all we get is this input, right? So we've essentially taken the high frequency and we turned it into a way that we can send it as a low frequency signal. And that's how we're able to get high frequencies through the USB. Okay, so hang on. All right. This will make a lot more sense. Now, of course, we're losing some of that data when we do that. However, if we use both a cosine and a sine wave, we do the same thing with a cosine and a sine wave, and save both outputs, we can recreate the original signal. So we do the same thing again, only twice. One with we take the data in from the antenna over here, and then we split it. So one goes through a cosine signal, one through a sine wave, a cosine wave and a sine wave. We do the same thing again. We go through a low pass filter on both sides. So we only get the lower frequencies. And then the ADC, this is analog to digital converter, basically taking the analog signal, turning it into a digital signal. And we get something called I and Q out. So like a stereo waveform, essentially. And I means in phase, and Q means quadrature. So in phase for the cosine, and quadrature for the sine wave. And you'll see this a lot in SDR. And that confused me so much when I started SDR. There was this IQ, like save IQ data. What's IQ? Well, now you know. It's the way that we get data into the SDR so it can pass through the bandwidth of like USB. And all software-defined radios, I don't care if it's in your Wi-Fi system, I don't care if it's in your phone, they all do this. They all take in a raw signal, they multiply it by a sine wave and a cosine, and then they get I and Q and out. And that's what they work with. They're all drawings. And next slide. So as I said, yeah, I stands for in phase and Q stands for quadrature. And now the nice thing about I and Q, and this is why we use, and this is very important for digital transformation, is that we can plot I and Q on like a circle, right? So we have I over here in the x-axis and Q on the y-axis. So yes, OGTV use the same IQ scheme. I imagine so. And like I said, any digital information, anytime you have an SDR, it's using I and Q. Like I said, your Wi-Fi router does, your phone does, they all do. So you're not getting one signal in, you're actually getting two signals in. The I and Q, which combine together and make the original signal. But actually INQ is really useful because now we can plot it. Like I said, you can plot I on the x-axis and you can plot Q on the y-axis. And there's so much we can do with this for like encoding data, for example. Remember how I was talking about phase and how that's super important for digital? This is why, because we have the I and Q coming in. And so based on the phases coming in, we can encode data. So here we have something called quadrature phase shift keyring, or QPSK. This is a very popular form of data transmission. It's used in Wi-Fi. It's also used in, of course, spacecraft. Basically, it's pretty universal for digital transmissions. And the way it works is that, so you have Q going up and down here, right? This is Q on the y-axis. And then you have I on the x-axis. And then you use something called a phase lock loop to read the data during different phases, or during the same phase every rotation. So it's, if you read, for example, at the first, you read it first and it's in the I and Q is in the upper right quadrant, you have a 1 and a 1. If it is, for example, you read it and you have I and Q in the lower right quadrant, it's at a 1 and a 0. And you can encode, 2 bits at a time. And the nice thing about this is that if there's a lot of interference, that's fine, because you have all this space over here to deal with interference. You need, the more advanced these things get, the less resistant they are to interference. But for a BPSK, which is just 2 sides, and QPSK, which is the quad, the 4 squares you see, they're very immune to interference. But you can encode a few bits at the same time. So you can get a lot of data through using these types of encoding, using phases. Let's clear again. And yeah, so you can use, we can see this in SDR Sharp. SDR Sharp is the common program used for listening to software-defined radio. And you'll see it, hold on, in this screenshot, let me, down here. So right now what I'm doing is I'm demodulating a satellite called Meteor M2 that uses a QPSK to send a digital signal back down to Earth. And you can use the same antenna that I talked about earlier. But you'll see that there's the four lines here, right? The four phases it can be in. And of course, there's some interference. We're talking about signals from space. So it's kind of all, spread out around here. But there's clearly a pattern, right? Like most of the signals are in the center here, and you can clearly tell where everything's supposed to be, right? So if a signal's in this quadrant, it's supposed to be a, what was it? 0, yeah, 1, 0. So if there's a dot down in the lower right quadrant, so in this one, all those correspond to like 1, 0 in binary. So it just gets those dots over and over again, and then creates it demodulates the signal back into binary. And so you can get some pretty good images using this digital encoding. Now, unfortunately, when you listen to it like you do it like an FM, demodulation, it just sounds like nothing. It's all just phase stuff on the base carrier. But you do get much better images using digital modulation. And so if you have less interference, you can do some really cool stuff with this. And this is how Wi-Fi works. If you have a strong Wi-Fi signal, you'll incorporate amplitude with phase modulation for something called QAM, quadrature amplitude modulation. So if you have a signal, for example, that is, let me change the color here to blue. If you have a signal that is very, high in amplitude, you're going to get a dot in like this area, right? You're going to get a dot in that area, and that corresponds to 0, 0, 0, 0, 4 bits. Oh, that's a lot. But of course, if you have a signal with low amplitude, you'll get a signal down here, and that's like 1, 1, 1, 1. So you can actually encode 4 bits at a time, and you get to like, I think this is 16 QAM, you get to like 128 QAM. And the way your Wi-Fi router works is that if you have a good signal, it'll use something like 128 QAM or 256 QAM. But if it has a weak signal, it'll use something like the base Q PSK that we saw earlier. So something like this. So if you have a weak Wi-Fi signal, it'll fall back to something like this for an encoding. But if you have a very strong signal, it'll do something like this. And that's how pretty much all digital communication works. Yeah, we do have a project where we decode a BPSK signal. So it's just 2 sides. But given the time and the complexity of that, I'm going to skip that for now. But we do have a project about that. So let me clear all the drawings. So far we talked about grabbing images from low Earth orbiting satellites, and that's a lot of fun. However, of course, you have to wait and you have to plan out when they're going to fly overhead. There are weather satellites that are in geosynchronous orbit. So they're always up in the sky. You can get them anytime where you're just not getting too much interference. And the 2 most famous of these are GOES 16 and 17, otherwise known as GOES East and GOES West. One is over the Pacific Ocean, one is over the Atlantic Ocean. Obviously, we would be going for GOES West or GOES 17. And like I said, these are geostationary satellites. Now, unfortunately, because they are so far away, geostationary satellites are, thousands of kilometers away. You need a dish to amplify the signal or boost the signal. Let's just put it like that. You need a dish to grab it. Now you can use a 2.4 gigahertz Wi-Fi dish and modify it. And there are lots of examples of this online. GOES uses 1.7 gigahertz. So it's really close to 2.4. And this is actually my dish that I use at the moment. That's my dish. Pointed actually at GOES 17 right now. And it's just, like I said, a modified Wi-Fi dish. But you can get some really cool images off GOES because, like I said, it's 24/7. It's far enough away. You get a full disk image of Earth, and these are actual images that I pulled off of that satellite. So for these images, the one on the left, of course, is Earth straight above, and you can actually kind of figure out where the satellite is based on where you're looking at Earth. And the image on the right is a close-up of Alaska. And of course, there are satellites beyond Earth orbit too, right? We have Mars orbiters, we have Voyager 1 and 2, we have Juno projects. Let me see. So are these things like XM weather get their images? Yes. So actually, if you go online, so I did this the hard way. So the hard way, of course, is to get an antenna like this, set up something like GOES tools. There's a GitHub page for it, and get the images and decode the HRIT signals. By the way, GOES uses BPSK, so bi phase shift keyring. So 0 on the left, 1 on the right, essentially. I did it the hard way. GOES has, or I should say NOAA, who operates these satellites, has all the images to download online. And if you were to go on to, for example, zoom.earth, that's actually where they get the images to do that. It's all shared online. It's all free. You're not breaking any laws by downloading the images. You're just learning how spacecraft works. Okay, let's talk about the deep space network. So we talk about the internet a lot on Earth for our network on Earth. But beyond Earth, there's the deep space network. So that's like the internet for everything that's not on Earth. All spacecraft beyond low Earth orbit is on the DSN, or beyond, I should say, geostationary orbit is on the DSN. And the way it works is that we have a few listening stations in 3 areas of the world that are 120 degrees apart that look at all parts of the sky at any given moment. So one is in Goldstone, California, one is in Madrid, and one is in Canberra, Australia. And thank you. Samuel has a link to some GOES images. Excellent. so the way it works is that you have a image coming from, for example, space, and depending on, what is listening at the time, it can pick it up and then relay it to each other. And the reason why you need a special sort of network for space is because stuff just gets lost up there, right? You don't know if you're going to get a good signal through. You don't know if you're going to get a pass ready where you can send the data down. You need a network that is going to be very tolerant to these sort of things, and that's where delay tolerant, and that's where the DSN comes in. And you can actually view the DSN live right now, like what it's doing, straight on the internet at eyes.nasa.gov/DSN. You can actually see what it's doing it right now, and maybe it's probably right now they're talking to Mars because of the rover there, but you'll see what it's doing. But yeah, so the reason why we need this is because we really need the data to be resilient to delays and disruptions. And so on the internet on Earth, of course, we use TCP/IP. What makes the Deep Space Network different is that they use something called DTN, or Delay Tolerant Networking Protocol. And there is once again, an activity you can do where you actually set up DTN at home. I think Sam created this a few years ago. You can actually have two Ubuntu or two Linux computers talk to each other using DTN. I mean, it's not any different than TCP, but it's just a different protocol that you can use. And of course, if you have the space and if you have the money, you can listen to the DSN yourself. There's absolutely no reason why you can't set up a big, 2-meter satellite dish and start listening for signals from deep space. And there's a big community that does exactly that. And so, yeah, let's talk a little bit about FPGAs. Let's segue. Let's see, M602 ion DTN. Yes, thank you. Sam has a link to the project. Let's talk a little bit about FPGAs and stop talking about radio for a second. One of the differences between what you see in space and what you have on Earth is that most things on Earth, of course, come from mass production. So you produce, 2 million Dell laptop computers, and they go out and they do their thing. In space, everything is usually fairly custom. So you're going to find a lot of custom hardware on spacecraft. And the way that custom hardware is developed is through something called a field programmable gate array. So if you really want to know like the hardware on top of on spacecraft, you really have to know what these field programmable gate arrays are. And essentially the way they work is that you have a bunch of inputs connected to what are called control logic blocks or configurable logic blocks. And each configurable logic block comes with something like, a logic table, some flip-flops, and you just sort of program each one, and you can use that to create gates and connect the gates together. And pretty soon, if you have enough of these CLBs, you can make your own custom microprocessor. And oh my God, that is so cool. And you absolutely need these in space because there's, like I said, you're throwing up one goes 16 and one goes 17. You're not making a mass production run of these. And some of the earlier FPGAs, you can actually see the dies. They were big enough that you can see each control logic block in this image here. So if you look really carefully, I know it's hard to see, but one of this early FPGA has each little logic block here that's barely visible, but definitely there. Are they remotely programmable? Yes, they absolutely are remotely programmable. That's the other thing too. Because so many things can go wrong, sometimes you need to fix the hardware on the spacecraft. So that's one of the other benefits is that not only can you reprogram them and make custom hardware on the ground, but you can reprogram them in space to fit the needs of what you're trying to do. So if there's a change in in the mission, and there almost always is because things go wrong, you can reprogram these devices. And so I would have an FPGA demo. In fact, I have my board out right here. I don't know if you can see that, but the software is not running on my system currently. Needless to say, I can configure this device. This is about $150. The center chip here is a standard FPGA, and I can configure this into a system on a chip. It's possible actually to use these FPGAs and recreate older systems. So I can, for example, put the code on here that turns this into an actual Apple II computer, like not emulating, like actually create a 6502 processor on some of the logic blocks, and then connect that up to like a video output and actually create an Apple II on here. I mean, there's a lot of stuff you can do on these. And if you have not heard about it, there's something called the MISTER project, M-I-S-T-E-R. It was first, it originally stood for MIST, the Amiga Atari ST project, but it sort of grew from that. And it's this entire collection of cores of old computers and consoles, like the Super Nintendo, the Amiga, of course, the Atari, Macintosh Plus, that run on FPGAs that you can buy. So let's talk about operating systems in space. We do not use Windows on our spacecraft. Now, Windows is absolutely in play on things like the International Space Station, as is, I think, iOS. I've seen some iPads on the ISS. But in terms of like spacecraft, our spacecraft are not going to be running Windows or Linux, with the exception of that Ingenuity copter. That Ingenuity copter was running Linux, but usually they don't run Linux or Windows. It's something else. And what is that something else? It's called a real-time operating system. So why is that important? If you are running a rocket, and you're trying to make very precise maneuvers, every millisecond counts, and you can't have your rocket fire for a few extra milliseconds because the operating system decided that now would be a good time to defragment the hard drive, or switch to something else really quickly. What a real-time operating system does is it allows you to specify very specifically when you want programs to run and when you want the background applications to run. And you can set it so that if you have something that's time critical, like a rocket, going off, you can do that. The most common one used in space is Wind River VxWorks real-time operating system. This is all over the place in space. If you have a spacecraft, I can assure you, there's about a 90% chance it's running VxWorks. Unfortunately, you cannot buy this, normally. There's no free version, but that's what's used. But there is free RTOS, which is put out by Amazon. And actually, the reason why I had this out is because I have free RTOS running on a CPU on this, but unfortunately, it's not running right now. But yeah, free RTOS. If you want to play with a real-time operating system, free RTOS is available to use, and I would highly recommend that one instead. And of course, let's talk about the software involved. We talked a lot about the hardware, how the signals get there, what it's run on, but what software is being run on spacecraft. And almost all of it is open source, and so we can play around with it, which is very nice. So mission control software. We all have seen the images of NASA, their mission controls. And a lot of people are wondering, what are they running on the big screens, and what are they using to monitor their spacecraft? The most common one is YAMCS, Y-A-M-C-S, or yet another mission control system, YAMCS. It's YAMCS. It just displays things. You can check it out at yamcs.org, YAMCS.org. The other one is OpenMCT, Open Mission Control something. That's another one you can use. It uses more of a web page interface to monitor missions, but you'll see these all over mission control stations. And the biggie that is on everything is the core flight system. Once again, another big open source project hosted by NASA on GitHub. Core flight system is on every spacecraft. It's what controls every satellite. It's what controls every rocket. If you do any drone work, you'll know that drones, for example, have a project called ArduPilot, which is like an open source drone piloting piece of software that's on everything, right? You can't escape it. This is the same thing, but for space. I can't think of a single satellite or a single spacecraft that does not run core flight system. If you want to know how how these systems operate, core flight system is the way to go. Unfortunately, I do not have a project with this yet, but I am definitely going to make a core flight system project for everyone to do in the future. And yeah, so let's talk about the current projects and where things are in the community. Oh, we have a question. I don't think we have any ransomware in space yet. Yeah, that's the other thing too. So most ransomware, like I said, most systems in space do not run Windows or Linux. They run a real-time operating system, and there's usually not many files in space. It is absolutely possible to take over a satellite and take it for ransom, I suppose, in some way. Maintaining it under your control will be difficult, but it is technically possible to do that. The issue is that it would create an international incident for sure if someone were to do that. It's sort of like, how everyone's up in arms about the recent oil situation, the pipeline situation. It would be like that, but at like 1,000-fold. If someone went after satellites like that, it would be a huge. I don't think that the potential profits outweigh the cost of creating that. Interesting, says Unstable. We can harden against Gamma X, but we can't. We're still vulnerable to crypto hacking. Yes, absolutely, because of course we have to get the data in. And like I said, if you get a satellite in an inoperable state, it will drop all encryption and try to communicate as best it can back to base. So it's absolutely possible to undo the encryption on any or most satellites and get access to it. Now, of course, the problem is that you need the command dictionary right away. People are going to notice if the satellite starts misbehaving. So if you were to do an attack like that, you would have to have the command dictionary ready to go and ready to send up the commands right away. And if you don't have that, then mission control is going to regain control of the satellite as soon as possible. Is it possible to send a corrupt update? Yes, absolutely. Once again, you would have to know the command dictionary of the system though in order to do that. So one of my current projects is making a azimuth elevation rotator. One of the things with tracking satellites is you got to track satellites, and you have to track them pretty precisely. For example, earlier we were talking about the NOAA 15, 16, 17, and their APT transmissions. Well, those are nice for us to learn how to do space hacking because they're easy to get. They're meant for the general public. Those satellites also, believe it or not, send down high resolution images on another frequency. Unfortunately, that requires precise tracking of the satellite using a rotating device. That has to rotate, left and right or azimuthally, and up and down or through elevation. And those are not cheap. Oh my gosh, there's only one on the market I can think of that's put out, and it's like 800 just for the rotating part, and another like 400 for the computer control, and it's just ridiculous. But this guy came along, ham radio. I'm going to say this a lot. If you want to learn about space hacking, first thing to do, get your ham radio license. Join a ham radio club. This guy made one using some standard servo parts, and put up the code. His name is his code or his ham radio operator call sign is WB0OEW. And he made this and proved that it's a doable concept. I was actually thinking about this for a long time, but I didn't want to invest like $500 only to find out that it can't be done. So this guy has a working prototype, but I thought, hey, this is cool. It can be better. So like, let's see some of the stuff that this person did on his design. Is that he put, for example, this device here, which is a magnetometer or accelerometer, which tells where it's pointing. It's attached by rotes on a PVC pipe. We can do better than that. And it is kind of rotating off center here. You can see how it's kind of lifted up, off. Like the gear is here, right? But it's rotating off center, which is going to add extra. It's going to need extra torque. But we can do something better. So what I'm working on right now is this idea right here that I threw up in CAD, and I'm currently waiting for all the pieces to come. But essentially the way this works is that it's the same idea. You have two motors. One rotates around a central point here for the azimuth. And then there's another motor here that spins this rod that will do the elevation. And what this does a little differently is that, one, there's more support, but also you'll notice that everything is nicely squared off. So I'll probably pin the accelerometer compass thing on top here. And it's all made out of metal. There's no PVC pipe, and everything will be nice and counterbalanced. So that'll be cool. And let's see what else is going on in the community right now that was big. There was SpaceX. So it turns out I didn't do this. This was not me. These were other people. They did a Falcon 9. They recorded the signals from Falcon 9 and figured out that it was actually sending an MPEG stream. So they ended up getting the raw data from the Falcon 9 rockets that were going up and getting things like internal tank data, images like of what's going on inside the tanks of the Falcon 9 rockets. And apparently SpaceX did not like that because now these Falcon 9 video signals are all encrypted. This person, Root, was the main person behind the Falcon 9 decrypting of the data. It was just an MPEG stream, probably encoded using BPSK. But yeah, they no longer let you do that, unfortunately. Yeah, so sad. And if you have an amateur, Samuel says, if you have amateur radio ham license, you can point an antenna at AMSATs. Yes, amateur satellites. Yes, if you have an amateur radio ham license, not only can you receive from space, you can send from space, including the International Space Station. The International Space Station has ham radio equipment on board intended for you to use. This is not like, oh, they have it, and if you are a hacker, you can get on there. No, you can use the equipment on the International Space Station to send data. And that was actually last month's project I was working on, which was a way to stomp out other people trying to stomp me out on the getting access to the International Space Station. So yes, absolutely. But yeah, fun's over. And then, yeah, so that is the end so far of the presentation. Do we have any questions before we go on to some of the projects? GM writes, does your org hire part-time consulting contractors doing part-time work? How does someone get involved with part-time projects at your org or similar? So my organization, the Telegraph Company, which does a lot of space things, hires a lot of interns. And if you are interested in a field that is related to telegraphs or space, you can absolutely apply. And we take in a lot of interns. And the interns are really surprised us sometimes. A lot of them they come in and I'm like, oh, I'm gonna have so much to teach them. Oh, this will be great. And then they come in and I'm like, well, this person kind of knows everything already, So yeah, definitely interns are a way to go if you want in. Chris writes, Travis Goodspeed did a neat talk a few years ago, roughly called Hillbilly Tracking of Lower Satellites on YouTube. Oh, I will check that out. So the way that we track satellites in orbit is we use something called TLEs, or two-line elements, and there is a project for that, and we'll get into that if we have time. But use everything in orbit is tracked on the ground and then relayed using these the TLE two-line elements, which is just a text file with 2 lines and a bunch of numbers. And with that, you can tell where everything is in orbit. Does my company, NTT, contract for NSA or NOAA? That's a good question. I do not know. Yeah, I don't know off the top of my head. I am sure there are contractors at the NSA and at NOAA. So, and keep in mind that there are multiple contracting companies. Oh, thank you. Sam posted a link to the Travis Goodspeed's blog on hillbilly tracking of low Earth satellites. This person made another azimuth elevation rotator. Oh, excellent. Yes, these things are absolutely required. Once you get up to a certain point in space hacking, you are going to need an azimuth elevation rotator to track satellites. It is, yeah, you absolutely need one. Like I said, you just can't grab signals off certain satellites by hand tracking. It's just too hard. You need something that knows where it's pointing and where the satellites are. Anyone want to tweak photography rotator for radio work? I think that's a great idea. Let me tell you actually what I'm using. Let me switch stop share. So one of the issues with these kind of projects with the rotators isn't so much getting it to rotate, but getting it to rotate with enough torque. These antennas weigh a good amount. So if we go to, for example, Servo City. Servo City is my robotics. So I'm not paid by them. I swear, I'm not trying to sponsor them. But if I need to build a robot, I just go to Servo City. And they have some high torque servos, servo gearboxes, all ready to go. And this is the one I'm actually using, a continuous rotation, 8 RPM, 720 gear ratio. And so this will actually, and the reason why I want to use this is because it has a saw torque of 2,450 ounces per inch, or 176.4 kilograms per centimeter, or kilograms, yeah, kilogram centimeter. And because you need to kind of lift up these sort of heavy things that are on rods, and it just needs to have enough torque to do it. Speed's not an issue. You just have to have enough torque to get through gravity. But definitely anything that can rotate is fine. And a lot of camera rotation equipment, like you would find in Hollywood, is made by going to Servo City and then constructing the equipment. So absolutely. Let's see, what do we have? Do we have any other questions? Do I want to, oh, Sam asked, do you want me to give you my Twitter? Yes, I want to give you my Twitter. Sam is wanting me to promote myself. My Twitter is Kaitlyn Guru. Kilo Alpha India, Tango Lima Yankee November, Golf Uniform Romeo Uniform. What are my thoughts on Blue Origin? I have some conflicting thoughts on a lot of the private for space endeavors. On the one hand, I really think it's having the private industry is good for competition and getting things up cheaply, which is one of the big hurdles in space, is how do you get stuff into orbit cheaply? And having that competition is good. Unfortunately, for a lot of the people owning these companies and their plans, I don't really like how it's concentrated among a lot of the billionaire class, right? The Elon Musk of the world. Their plans for space travel is sort of like, well, Earth is doomed, let's go to Mars. Let me tell you right now, you do not want to live on Mars. Mars is terrible. If I were to tell you, hey, let's go live on the North Pole, and have no way to get back, that's kind of what it's like living on Mars. I'm not exaggerating. It is not fun. And then of course, billionaires have their own billionaire quirks and stuff. Anyway, here's a link to my Twitter. I'll post in the chat. Once again, KITLYNGURU to everyone. Let's save Earth and not move everyone to Mars. And of course, the society that Elon Musk and everyone wants to set up on Mars is very much where they maintain power. Hundreds of kilograms isn't so much. Yeah, I've been playing with some 60 kilogram servos. Yeah, it's not much. I mean, definitely it's not much. You need as much torque as you can get, and it's hard to get that much torque. I never thought of that. Yeah, no kings on Mars. Yeah. When it's time for humanity to start populating outside of Earth, I would hope that it's more of an egalitarian effort rather than being sort of endeavored by people who have a lot to lose by egalitarianism. Let's just put it like that. It might be like Lord of the Flies. I would hope not. On Mars, Lord of the Flies would be even worse than Lord of the Flies on Earth. There's just nothing there. It's desert. Let me tell you about Mars. Mars is, like I said, a desert, but it's not a warm desert. It's a cold desert. The Earth has about 75% more mass or something. So it's a lot less gravity, about 30 or 40% the gravity of Earth. So you're going to lose some bone density and stuff being there. But what's really bad, of course, is there's not much of an atmosphere. And it's not just that the atmosphere is carbon dioxide. Everyone knows that there's no oxygen on Mars, or very little. But what makes Mars really kind of annoying is that there's 1% of the atmosphere on Earth. So there's almost no atmosphere. In fact, that's why Ingenuity was so ridiculous. It's that Mars is almost a vacuum, and they still got Ingenuity to fly, and that was really cool. But there's almost no atmosphere. Terraforming is just not going to work anytime in the near future. In the next 100, 200 years, we're not terraforming Mars, okay? It's not happening. There's very little water. It's a dead planet. And the most difficult thing about living on Mars is that there's no magnetosphere. The core cooled a long time ago. So of course compasses won't work, but more importantly, there's nothing to stop radiation. If you want to live on Mars, you got to live underground. You can't live on the surface. There's just way too much radiation. You'll just get irradiated and get cancer, and that's not good for anyone. So it's going to kill you not only through the lack of atmosphere, through the lack of oxygen, but it's also going to irradiate you to death. So yeah, have fun with that. Some people are naysayers, but Elon Musk is going to Mars. We're going to go to Mars. That's for sure. It's just Mars is not a substitute for Earth. It's that simple. We're going to go back to the moon for sure. We're going to go to Mars. But the idea of like a Mars colony or even like a moon colony, no. That's no. Do you know if SpaceX has become an Elon Musk crypto investment company scam too? No, SpaceX is doing things. Their Falcon rockets really work, and the way that they land and save the rockets. That's really awesome. I mean, like I said, they're doing some good work. I mean, the thing about Elon Musk is that he's not an inventor. Okay, he is a business person. He's sort of like almost Steve Jobs, kind of, but not really. Like, he's really good at marketing. Like, of course, Steve Wozniak created Apple, and Steve Jobs hires engineers, or had, when he was alive, hired engineers to work on all the devices. And he just marketed them. And Elon Musk is sort of the same way. Like, Elon Musk doesn't design rockets. His ideas are actually kind of dumb, to be honest. Like, not just his living on Mars, but like his transportation systems he wants. He doesn't like people and wants like tunnels underground and stuff. And no, but he hires good engineers, right? He hires good engineers at Tesla. He hires good engineers at SpaceX, and they produce viable products. Okay, the Tesla's a fine car. It does its thing. The Falcon is a great rocket. And their newer rockets are going to not blow up one day, and they're going to be fine. So good times. Putting Bitcoin profits on the Tesla profit sheet, pump and dump. Yeah, that's sort of, yep. Tesla is trading crypto. I don't know anything about that. Yeah, Tesla's not a scam. SpaceX is not a scam. Tesla is sort of a scam lately. They lost some money on the cars and made the real profits by manipulating the cryptocurrency markets. I didn't know that. Yeah, one of the issues, of course, I have with a lot of the cars, and this would be a great talk for a car hacking talk, is of course that they are now putting in-app purchases in cars. If you want the extra deluxe version of the Tesla, you pay like a subscription fee. Can we have a car hacking class? Yeah, I know someone who would be perfect for that, for teaching that. Her name is Elizabeth Biddlecombe. And yeah, hacking Teslas is definitely something we should be doing. Lots of cool stuff. By the way, if you have an SDR and you get good at radio hacking, a lot of the car unlock systems use, of course, radio communication. So if hacking satellites is a good beginning introduction to car hacking in a way. Ad blockers on cars, can't wait. Yeah. Yes, exactly. All right, so we've kind of gone off topic here. Let's look back at the scoreboard. Let's see if anyone is playing the CTF, and if we have time, we can do one together. Let's see. Here we go. Oh. Let's look at the scoreboard. Oh. Looks like no one is playing. That's fine. That's fine. We can. That just means that my talk is very interesting. Someone has been distracting them from. Yes, someone has been distracting them from the CTF. Yes, that was me. So we can do a few of the CTF problems together. Let's go back to the main space hacking page. Okay, there we go. We sure are playing, huh? Why is that not showing up? Huh, scoreboard is not working. Shows up on recent points, but not the scoreboards. Huh. Looks like someone made a mistake. I should probably be docked pay for this. I will dock my pay. All right, so all right, let's do a few of these together. So let's talk about GNU Radio. GNU Radio is the way of sort of interfacing or programming SDRs using custom software. So if you get a signal and you want to figure out like what it's doing, there are two popular programs to do this. One is Universal Radio Hacker, which a project will be coming soon. But more importantly, there's GNU Radio. And if you had to learn one or the other, I would say go with GNU Radio. And basically what this does is it lets you visually program your software-defined radio. So if you get a signal, you can tell it how to decode it. And so it is a difficult install on Windows. On Mac or Linux, it's pretty easy. But on Windows, there's a big, you have a few options. So I did, I think, yeah, so today I used the Geoff installer. There are a few other installers you can use. But yeah, I just downloaded GNU Radio 3.8 and installed that today. And let me boot it up. Should be here somewhere. EF GNU Radio 3.8. So we're starting up GNU Radio Companion, and this is a GUI, so it's really nice and easy to use. Let's see, I saw something in the chat. It may be possible for you to get hooked up here, playing off some old NASA and NSA facility. 2 meters. Oh, nice, nice. Yes. Yeah, there are a lot of places that around here with a lot of dishes that I really want to get hooked up with. I know Stanford around here has some really cool radio equipment for doing like moon bounce stuff. Yeah, I mean, yeah. If anyone knows any cool resources for like big telescopes for space hacking, yeah, keep me informed. Definitely always on the lookout for that. So yeah, let me share GNU Radio Companion. Oh, here it is. GNU Radio Companion. Here we go. So this is what GNU Radio Companion looks like. Basically, you have this center area. Oops. This center area here where you're going to like essentially draw what the radio pathway is. So the way radio works is, of course, you grab a signal from an antenna. So you have like an antenna over here that comes in, and then it gets processed in some way. So you might like demod it, decrypt it, et cetera, through a big pipeline, and then you get something out. And we're going to sort of draw that pipeline in this area. And so if we go back to the project, I know you can't see this. But if we go back to the project, we're going to start off by making a new project, and we're going to go into options. So in GNU Radio, if you see something red like this, that means something needs to be edited, something's wrong. So we're going to options, and we're going to set the ID to something new. So we're going to set it to tone. We're going to make a tone generator. ID is tone. And we'll go to OK. So notice that ID is no longer red and options is no longer red. Okay, excellent. So now we're going to create a tone in GNU Radio. Remember when I was talking about software-defined radio and like the I and Q, and we're mixing a sine wave with a cosine? A lot of times in radio, you do need to create some sort of like wave or a specific waveform. So we're not even going to grab anything from the radio right now. We're just going to create a tone. So to do this, we're going to go over to waveform generators over at the right side here. And GNU Radio has frozen on me. Hello? No? Let me stop sharing. Maybe that'll fix it. Yes, that fixed it. Okay, so sharing apparently makes it not work. That's interesting. Okay. All right, so we go to waveform generation, and we're going to go to a signal source. I'm going to just drag that on. Oops. Drag it. Oh, there we go. Double click. Awesome, awesome, awesome. So we're going to double click on the signal source. We're going to set it to what we want it to be. Complex output. Once again, think of complex as IQ. We don't want IQ out. We want just a simple floating point sine wave. Keep it simple. And a frequency of like middle C, like 261 hertz. We'll say, yeah, cosine float. Yep. Okay. There we go. It's still red. Why is it red? Because I didn't set stamp rate. Oh, I did set it to 3200. maybe because nothing's coming out. All right, and we'll need an audio sync. Oops, let's see. Port's not connected. Yes, Chris got it right. I don't have it connected to anything. That's why I tried. So we'll need an audio sync. Let me once again stop the share so I can use it. Sorry about this. Core audio sync. There we go. Now I'll share again. All right, so now we have an audio sync and a signal source. And we just drag from the output to the input of the audio sync. And if we run it, we'll get a tone out. So we have to save it first. So I'll save it on my desktop. Temp. Warning, missing Xterm executable. Okay. Oh, there we go. Anyway, we get a tone out. And I have no idea how to stop it at this point. Run. Yeah, there we go. So yeah, so we managed to successfully create a tone using GNU Radio, using these blocks. So as you can see, there's no programming required necessarily. However, I will say under the hood, what it's doing is it's creating a Python script using what we draw on the screen. So if there is more complicated programming that's necessary, oh, I see Chris is an expert. Clicking on the ports will connect them. You don't need to drag the wire. Yes, yes, you can do that as well. So if you click, you can connect them together, just like that. And of course, you know, we heard it, but when you're working with radio, it's sometimes nice to have a visual representation of what's happening. So we can add a QT time sync, which will give us a nice graph. What's being put out to the audio. Let's stop the share once again so I can use the side panel. So that is in instrumentation. Let's see, core instrumentation, QT. Of course, QT, for people that don't know, QT is a standard GUI library. QT time sync. There we go. We'll say type, let's actually go back to sharing now that it's in. Where's sharing? Oh, there we go. So we have a time sync here. We'll set the input to float and set the output to the input here. And now when we run it, not only should we hear the audio signal, we should see it. There we go. Oh, there we go. Now we can actually see the waveform. Now, and we can close it. Yeah, and so the rest of this project, let me switch back to, once again, back to the web browser. Share web browser. And so in the rest of this project, you'll actually create a scroll bar and you'll be able to change the frequency that's being generated. And you'll end up with something like this, where you have a sine wave generation. And you can control the tone and the frequency. And like I said, underneath the hood, what it's doing is it's actually creating a Python script that you can edit. And that can be really useful too, because you can create the basic framework for how you're going to decode the signal, and then edit the Python that comes out. All right, I just noticed it's 4:01. Any more questions? So yeah, like I said, GNU Radio is one of the go-to pieces of software for hacking satellites. If you do not have a piece of software that will decode what's coming off the satellite for you, GNU Radio is usually going to be your first step to getting that working. All right. Well, it is 4 o'clock. I do want to point out, I realize that I've spent all this time talking about SDRs and I never showed you one. This is what one of them looks like. It's just a little USB device, 20 bucks on Amazon. Your antenna goes on, sorry about the green screen. The antenna goes on this end. And of course, USB goes on the other end.
Thank you very much. That was an incredible presentation. Any other questions? Okay.
Yeah, and before I go, let me give you a pro tip. If you get into using a lot of SDR stuff, I mentioned the antenna. That's of course very important. But you also want something called a low noise amplifier. And you also want to have a filter. Those are going to help you a lot. Just a pro tip. If you're having issues, amplifier and filter. And you can actually go onto Amazon and get like 2-in-1s like this. This one is specifically for NOAA satellites. It's a low noise amplifier and a filter in one. So it'll filter out anything else that's not within the normal NOAA 137 megahertz, and also amplify the signal. Oh, we have East Coast members. Awesome. Thank you for coming all the way from the East Coast.
We have people from everywhere here. You did.
Excellent.
Yeah. Hope to see you soon in person in San Jose.
Absolutely. Like I said, I just moved to Sunnyvale. So I am going to be joining Pacific Hackers. It's nice to meet everyone.
Absolutely. Thank you very much again. And thanks everybody. Do you have, we have a Discord that I can actually publish the invitation here. If you guys want to join it, here's where we usually coordinate about meetings, and we're now coordinating about what we're going to do at DEF CON. I was talking to Sam about it when we started the meeting, and thanks Sam for hooking us up with Kaitlyn. This is awesome, and hopefully we'll continue bringing this excellent content, and thank you everybody for joining.
Great.
So someone asked if the talk will be available later. Absolutely. It was being recorded by 2 people actually. So yeah, I know we went over a lot. It's a lot to cover. But this is really the base information that you really need to get into space hacking. And like I said, most of this is just understanding what the radio is doing, because of course, that's how you communicate.